Today we're going to do implicit differentiation, but I want to start with this. What I'd like you to do in just a moment when I say go, I'd like you to leave your writing utensil and your notes on your desk, but I would like you to go find, you need to get out of your desk to do this too. You can't just sit there and talk to somebody. You got to get out of your desk and have a conversation with the person you worked with yesterday on the partner quiz, and I would like you to talk through the process of finding the derivatives 1 through 4. Just talk through the process. Talk about what rules you'd use. Talk about, you can use the notation, you can use notational language, say, well, I would say the derivative is, and then say it out loud, but I don't want you to write anything during this. And then after you've talked about the first 4, I'd like you to talk about 5 through 8. And then once you're done with 5 through 8, I'd like you to make some comparisons about them. So I would like you to take 2 minutes and do that without writing. You can't stay in your desk for this. You can stay where you're at, but you need to be standing and conversing with the person you worked with yesterday. Ready, go into what we're doing today. Walking through these quickly then. Number 1, derivative. We didn't talk about this one out loud yet, but the derivative with respect to x of f of x, we would normally write in a very concise way as f prime of x. That's just fine. We don't know what f of x is. It's the derivative with respect to x. F prime is a short way of writing that. Okay? So number 5 then, you could write as dy dx, or you could write it as y prime. Number 2, we agree is a product rule problem. So the derivative would be x f prime there, plus, what's the derivative of x? 1 f of x. That's product rule. We don't know what f of x is, but whatever f of x is, you'd put in there in parentheses as a substitution piece. Okay, number 3, or we should do number 6. Should we do number 6? Because it's like number 2. Would that be okay? Notationally, how might we write the derivative of xy? We could do it as x y prime plus x prime y, but what's x prime? 1. We know that one. So this would be xy plus 1y. Because x prime, if f of x equals x, the derivative of x is 1. Sorry. Thank you. Good point. X, y prime. My bad. X times y prime plus 1y. Or, and I'm going to use this sum today. This would be x times dy dx plus 1y. That's another way of writing it. That's the way I prefer, but there's other teachers that use a little different notation, and that's okay. We'll talk about that in a minute. Number 3, we agree that it is chain rule, so the derivative would be 2 times f of x, Tootsie Roll, Tootsie Pop thing, derivative of the outside, leave the inside the same, then multiply by the derivative of the inside. What does that look like if we have y's? The derivative, I'll slow down a second so you can catch up. You're frantically writing to keep up with me. Number 7's a little weird. It's just a slightly different notation. But if we think of y as f of x, we're going to use that same rule. Y is a function of x, so I'm going to write it as 2y to the first. I'm not actually going to write the first, because that could end up being confusing notation in a minute. I'll write it as 2y times the derivative of y. I'll write that as dy dx. Some of you might choose, there's an or, some of you might choose to write it as 2y y prime. We'll talk about the advantages and disadvantages of both of those notations in a minute. Question? Okay, question is, I thought dy dx was the same as d dx. As simply as possible, d dx is a command, and it's an operator. And we're going to talk about that in a minute. It's an operator. It's an operation. d dx is a command that says take the derivative of. Okay? So I can take the derivative of an expression, or dy dx is typically tied to something like this. So if y is 3x, dy dx is 3. Does that help? Okay, good. I lost my spot. There we go. All right. Last one. Both notations or just one okay? Just one? Left or right? The right one's new. Maybe we should do the one on the right. Let's do it. Let's do number 8. Chain rule first. What's the derivative of sine? Cos. Keep in mind it's a chain rule problem, so for the first part, I'm going to leave the inside the same. Cos xy times, now I need to multiply by the derivative of xy. We already did this. Do you remember what it is? You don't have to remember because it's up there, right? What rule? Product rule. So you could write it as x, y prime, plus 1y. The notation I prefer doesn't, it's not wrong either way, but I would write it as this. With dy dx. I'll talk more about that in just a little bit, why I choose that notation. Okay? So the question is, what's the point of this? Now I do this on purpose because what you're about to learn is a process called implicit differentiation. You're still going to use a lot of the same rules, but we're going to do it on weird functions. So it's going to look very different. The process is going to be a little bit funky, but I want you to know and make the connection between using f of x notation and using y notation, because implicit differentiation is really reliant on your ability to use the notation on the right side of this screen. Okay, so we're going to refer back to this as we go. All right, so go to the front of your notes now. Front of your notes. We're going to skip this class opener. It's a really good chain rule problem. We're not going to do it today. For the interest of time, we can come back to it later or talk about it if you'd like to. Here's what we're going to go through today. We're going to talk briefly about implicitly defined functions. We're going to define them, and I'm going to show you what they look like. I'm going to show you kind of the positives and negatives of them. We're going to talk about, we're probably not going to get to tangents and normals today. We're really probably only going to get to that one, but if we get to the other stuff, it's a bonus, and we might end up actually doing that on Monday. So, implicit differentiation allows us to differentiate some functions that we're not real familiar with. We're very used to writing equations as f of x. We deal with polynomials, we deal with square roots, we deal with compositions, all those kinds of things that end up really nice and have nice derivatives. But there are some functions called implicit functions that have derivatives that we need to be able to calculate as well. So, just as far as a definition, implicit functions, to put it simply, are not solved for y. Put it into a simple notation for now. Implicit functions are not solved for y. They're going to have x's and y's on the same side. They're going to have x's and y squareds in the same equation. And I put in here on the right, guys, it allows us to find derivatives of functions or not functions, because implicit equations are not always functions. Implicit equations are not always functions. And most good implicit equations are in fact not functions. Because if we could write them as functions, we probably would, because we like functions better than things that are not functions. Here's a good example. This is a good, simple example of an implicitly defined equation. X squared plus y squared equals 9. How many of you feel like you have some familiarity of what that might be? X squared plus y squared equals 9. It's an equation. Do you feel like you know what its graph might look like? X squared plus y squared equals 9. Thoughts? Go back a couple years. What is it? What's the graph look like if x squared plus y squared is 9? Take it back to higher algebra. Close. Kind of. Not quite a square root graph. Geometry. Looks like Pythagorean theorem, doesn't it? Don't remember? That's okay. You're all gonna be like, oh, in just a minute. You ready? Am I gonna be able to hear an audible ah in just a minute? It's a circle with radius 3, guys. Ah. Is that familiar at all now? Not at all. Not at all. You must have been in higher algebra the year they skipped circles. Okay. Well, we learned something. That's okay. That's a circle with a radius of 3. Okay. Now, tell me why. Just give me a real brief reason. Knowing that it's a circle, I'm making a circle in the air. Knowing that it's a circle, why would I not write it as an explicit function? Because it's not a function. And I can't write anything explicitly as a function if it's not a function. Does that make sense? So we're going to deal with funky equations that have x squareds and y squareds on them and are not, you can't always solve them for y. Okay? Let's go. Shall we? First example. xy equals 1 is an equation that is defined implicitly. Tell me why it's implicit rather than explicit. Simple answer. It's not set equal to y. That's it. It's implicit because it's not solved for y. Will you take 20 seconds on your own and make it explicit? Go ahead. Implicit means not solved for y. Some of you didn't even take 20 seconds. If implicit means not solved for y, explicit means solved for y. They are opposites of one another. What'd you get? You good there? Okay. So I want you to know this, some implicit equations can be written as explicit equations. Here's an example of one. Most of the good ones can't, all right? But I'm going to start with a basic one that can be written both ways for demonstration purposes, because I'm going to show you the process of implicit differentiation, and then I'm going to demonstrate with this example, not exactly prove, but demonstrate with this example that implicit differentiation and explicit differentiation are the same thing. We didn't call it explicit differentiation, but that's what you've been doing for the last 3 weeks. It's explicit differentiation, finding derivatives. The implicit differentiation is just going to be a little bit of a twist on that. Okay? So, will you take and just do part A there on the left? Will you write the derivative for that, please? Using the methods that you've been taught over the last 2.5, 3 weeks, will you write that derivative and then show your neighbor? Do you and your neighbor have the same thing? Do you and your neighbor both have this? Do you both have that? Could you have written it differently and it'd be the same? What'd you write? Some of you are nodding. What'd you write that was different but the same value? Those are the same thing, right? Okay, good. Now, I'm about to show you what is called implicit differentiation. Differentiation in math class means take the derivative. Implicit means it's not solved for y. So we're going to use implicit differentiation. So we're going to take a derivative of this thing on the right, of part B here, without solving for y. Okay? Now, this goes back to the idea which was the question earlier about what's the difference between d dx and dy dx. This is the big difference. What I'm going to do to this implicitly defined equation is I'm going to write a command on the left and on the right. Now, differentiation, the operator d dx, this is the operator, it tells me to take a derivative. That is, you can differentiate both sides of an equation and maintain the equality, just like adding 2 to both sides or dividing both sides by 3. The derivative operator, d dx, is something that you can apply to both sides of an equation and maintain equality. It's another one of those algebraic tools that you can do to both sides. Okay? So now I need to do the process of the derivative. What I did was on this step, I made the command, take the derivative. Now we need to take the derivative. Do you see why we opened with what we opened with today? What is the derivative with respect to x of x times y? You don't remember, but that's okay. What process are you using? I'm hearing some thoughts out loud. Product rule. I'm going to use product rule on the left. Okay, so let's go through it. X times y prime. I prefer this notation. Doesn't matter. I'll show you both of them in just a minute. X dy dx plus the derivative of x is 1, and the second function stays the same, so that's 1y. Equals. Now I'm going to do the same thing on the right-hand side. What is the derivative with respect to x of 1? Everybody in unison. 0. Good, because it is a constant. The derivative of a constant is 0. Good so far? What was our goal? Find. Okay, we differentiated the equation, but there's one more step in this. What does the command say? Find dy dx. Do we have dy dx yet? We do not. dy dx is here. If I'm going to find dy dx, the typical command find means solve for. What should I do? Solve for dy dx. What do I need to get rid of? Get rid of the y. That leaves me with x times dy dx equals negative y. Now what? Divide by x, so I get dy dx equals negative y divided by x. And of course, the answer we got for B is the same as the answer we got for A, right? Trying to help us process what we just did. Okay? Now, there's some confusion, right? You're saying, Mr. Best, they don't look the same. Now, this step is kind of the cherry on top of the sundae. You don't need to do this every time, but I want to show you that they are the same. We got this thing when we did it explicitly, and we got this thing when we did it implicitly. We have an advantage, and this only applies to really nice ones, where you know the explicit and the implicit equation. You're not going to be able to do this every time. But because I can write this explicitly, I know what y is. What is y? 1 over x. So because I know it explicitly, and only because I know it explicitly, couldn't this also be written as this? There's not very many moments happening right now. Take it a step further. Take it a step further. Isn't this negative 1 over x squared? Now, we don't always have that advantage, guys. We're just going to have to trust the process. So on the right, we did the process of implicit derivatives. On the left, we did explicit derivatives. And because we were dealing with the same equation, we got the same thing. Now, you're not, for the next several examples, going to have that advantage. Because most, like I said, most good implicit equations can't be solved for y. You can't make them explicit very easily. For example, 1. Doesn't that look fun, you guys? Okay, well, let's go through the process. Let's go through the process, and I want to try to break this down as simple as possible. Will you stop me along the way if there are questions? Am I still recording? Where'd my little record window go? There it is. Good, it's still going. I had a fearful moment there. All right. So, if you have an implicit equation, this is a really good implicit equation. Why? Because it's not solved for y. And just take like 10 seconds to look at it and think about how you might solve it for y. But don't take more than 10 seconds. Do you see that's not fun to solve for y? We took like 4. We good? Let's not solve it for y. All right? Let's implicitly take the derivative. So, implicit differentiation involves, let me use a different color. Implicit differentiation involves the operator on both sides. And I really think you should do this every time. You need to do it to both sides, otherwise it's not an equation anymore. Okay? Derivative of the right side? 0. I'm going to put it way over here, though, I think for obvious reasons. Okay? I'm gonna write another step in here, and you don't always have to do this, but I'm going to write another step in here because it's complicated. When I'm taking a derivative and I've got pluses and minuses, I'm really happy. Do you like pluses and minuses? Yes, because I can differentiate those parts and then add them together. So here's what I'm going to do. I'm going to write this as, this is just kind of a simplification step, and you're not always going to do this. But I'm going to just apply that derivative operator, quote unquote, distribute it. I didn't need to move the 0 over as far as I thought. We're going to need to move the 0 further over on the next one, though. Okay? That helps us break it down a little bit. All you're doing is telling your brain to simplify it down into some parts right now. If your brain can process all those things at the same time, good for you. My brain is not that advanced. Okay? Let's go left to right. Let's take this one function at a time. X squared sine y. What's the rule that dominates this problem? Product rule. Product rule. Okay? Bear with me. The first function is y squared. What is the derivative of sine y? Cos y dy dx. Why do I need the dy dx piece? Because it's the derivative of the inside, and y is an f of x, right? If this was sine f of x, it would be cos f of x, f prime of x, right? Okay. I'm not done with product rule on that, though, yet, right? Plus the derivative of the first. What's the derivative of y squared? 2y dy dx times sine y. I'll leave the second one the same. That is product rule for that piece right there. Yikes. Next one. I'm going to take the middle one here. Oh, that's a nice break, isn't it? What's the derivative with respect to x of x squared? Awesome. Nice break. Let's do this one. What rule dominates that problem? Product rule. Yeah. Do you want to put the 4 as part of the x, or do you want to do the 4 up front? Do you care? Put the 4 up front? That's okay. Now let's do product rule on xy. Product rule on xy gives us x dy dx plus 1y. Guys, I have good news. We're done with the calculus on this problem. We're done with the calculus. The calculus step is take the derivative. We took a derivative. Now, what do we need to do? We need to do some nasty algebra to get the dy dx by itself. Bear with me, will you? Continue to do so. Okay. Now, what do I want? Go ahead. Question. I insert the dy dx whenever I'm taking the derivative of y. It's a good question. Where do I put the dy dx? I insert the dy dx whenever I'm taking the derivative of y. And going back to the beginning, I had things like x f of x, and the derivative of x f of x was x f prime plus 1f, right? It's the same as doing this. It's x y prime plus 1y. It's the derivative of y. So I'm doing it as anytime that y needs its derivative taken, I'm going to put in dy dx. And it applies to the y squared because it's like f of x squared. It's a chain rule problem. 2 f of x times f prime, or 2y, y prime. Okay? Mm-hmm. Okay, going to y squared sine y, yep. Yep, okay. Y squared is the first function kept the same. Cos y dy dx is the derivative of sine y. It does, but it doesn't, because y is not an x. If it were sine x, its derivative would be cos x, because we're taking the derivative with respect to x. But since it's sine y, and I'm differentiating with respect to x, it becomes cos y. It's like cos f of x times f prime of x, because it's a function inside of a function. X is a variable, y is a function. Think of it that way. Okay? All right. Our goal now is to solve for dy dx, which means all of the dy dx's go on one side and everything else goes on the other. So let's group everything that's got a dy dx on it together on the left-hand side. So first thing I'm going to do, I'll go y squared cos y. I'm going to do a lot of rewriting here, guys. Dy dx plus 2y sine y dy dx. I'm going to skip the 2x for now. I'm going to write minus 4x dy dx. And I'm going to leave the other thing off for a moment. We good so far? I'm going to do an extra step now, though. What am I going to do with the 2x and the negative 4y? The 2x and the negative 4y. The 2x is blue, the negative 4y is red. The 2x is here, the negative 4y is here. If I want all the dy dx's on one side and everything else on the other, let's move them over to the other side now. Is that okay? So I'm going to do this. Negative 2x plus 4y over on the right-hand side. Good? I took this piece and I moved it over, and I took this piece with the distributed 4 and moved it over. Okay? Now, everything's got a dy dx. And if everything's got the variable I want, let's factor it out. Good so far? So it's dy dx times the quantity, yuck, y squared cos y plus 2y sine y minus 4x. Close parentheses equals this thing. Guys, don't worry about simplifying a whole lot. What are we about to do on our last step? Divide. So dy dx is equal to negative 2x plus 4y divided by y squared cos y plus 2y sine y minus 4x. Guys, that's an implicit derivative. It's done. Okay, now, you might ask yourself, Mr. Best, why do you use all the dy dx's? You could use y primes. And I'm going to use y primes for the next one, and I'll show you what that looks like, and I will tell you to be careful, and I'll give you a good reason for it in a moment. So let's take example 2, implicit differentiation. We're going to differentiate both sides with respect to x. First step is just going to be notational for me. I think it's important to write that operator, though. I'll go one more step, and I'll write this as and I'll do a derivative on the right-hand side. What's the derivative of 1? 0. Okay. I've applied the operator, but I haven't done any derivatives on the left-hand side yet. First one's easy, second one's a little more complicated. What's the derivative with respect to x of x squared? 2x. If you wanted to be really specific about it, it would be 2x dx dx. But what's dx dx? Which is 1. Yeah. Derivative of x with respect to x is 1. But you're using the chain rule. Do you need to write it? No. But I just want to show you that it works on that one too. So that's 2x. What's the derivative of y squared? 2y times y prime. Okay. Some people like to use y primes instead of dy dx's because it's easier to write, and I'm okay with that. The only thing I'm going to suggest is that you be very, very careful. Many of my students have a little bit of a difficulty expressing themselves mathematically, which means their apostrophes look like ones sometimes, and if you saw a y to the first in your work, you might just skip the y to the first and write it as y. You with me on this? If you write it as y apostrophe, you can do this. But if you write it as y and you think it's y to the first, then your derivative's going to be all screwed up. Okay? As long as you're careful, and this is a little bit of an easier example, I would advise you to be very careful up here using y primes, because gosh, if you write a little mark that looks like a prime and you forgot that you wrote it and it looks really small and you forget it, you're in trouble. Okay? But if you can be very concise and specific about your notation and know what you're doing when you're writing an apostrophe, you can be okay doing this. Okay? So I want to solve for y prime. What do I have to do? Minus 2x. So this is negative 2y, y prime equals negative 2x. Now what? Divide by negative 2y, and I get y prime is equal to negative 2x over negative 2y, more popularly known as x divided by y, and that would be dy dx. Now, the hard thing about implicitly defined functions is we now need two pieces of information in order to find a derivative. In order to find a specific derivative at a specific point, what I meant to say was a derivative at a specific point, I would need both the x-coordinate and the y-coordinate of that point. Whereas with explicit functions, all we needed was the x-coordinate. So implicit ones are a little bit different. We can talk about that again in a minute when we can go back to the circle example if you want. But if you think about it, if you have a circle, for any x value, there's two different derivatives you could find, right? So having the x value isn't enough to know what the slope of the tangent is, because there's a tangent here and there's a tangent here. So for implicitly defined equations, you need two coordinates in order to find a slope. Does that make sense? It's more of a conceptual thing than anything, because most good implicit equations aren't functions. Right? Let's do one more together. Example 3. You want to do 3 or 4? Let's go in order and we'll see if we need to do 4. Let's start with 3. Okay, first thing I'm going to do, I'm going to write the derivative operator. What rule is in play on the left-hand side? Product rule. Do you want to use y primes or dy dx's? Let's try y primes. We try y primes? Okay. So the derivative of x times y squared is x times 2y y prime plus 1 times y squared. That's product rule. Okay, so far? Derivative of the right-hand side? Derivative of x minus 8? 1. What am I solving for? Y prime, which is in place of dy dx. I want to solve for dy dx. In this case, it's y prime. What do I need to do? Subtract y squared. That gives us 2xy times y prime equals 1 minus y squared. Good? Last step. You can do it in one step. You know that, right? What do I need to divide by? Divide by 2xy. So y prime is equal to 1 minus y squared divided by 2xy. Oops, I need to write 2xy. And that's dy dx. Is that all right? Question. Okay, good. Question is, what does this tell us? It tells us how to find the derivative at a specific point. So just as a brief example, I'm going to take a shot in the dark here. I'm going to hope this works. I'm trying to find an x value that'll work really nicely here. I need x to be, let's say I had a specific x value. Let's say I wanted to find the tangent at x equals, I need to use something bigger than 8. So let's go with 10. Let's say at x equals 10. Okay. I need more information in order to find the derivative, because I could put 10 in for x, but I don't know what the y coordinate is. So I would then go ahead and do 10 y squared equals 10 minus 8 and solve for y to find out what the y coordinate. And this is not going to be a great example, but you can, 10 minus 8 is 2, 2 over 10 is 1/5. So y is plus or minus the square root of 1/5. You with me on that? And now we can tell with an x value of 10, there's two different y values, so it's not a function. So I would plug in the ordered pair 10 square root of 1/5 in for x and y, in for x and for y. That you can see pretty quickly that that's not very fun. Normally you'd be given a little nicer xy value, but I was making this one up on the fly. Or the other derivative would be found by using 10 for x, negative square root of 1/5 for y. Okay. So you might be asked to find the slope of a tangent at a specific point on an implicitly defined equation. And we'll go over some more examples of that on Monday. Okay? 4? Gonna do 4? Let's go through 4 quickly. We're not gonna do 5 today. It's review, but we'll talk about it again on Monday. All right. dy dx. Do you want to use y primes or dy dx's? dy dx's is good with me. The y prime guys got overruled. Sorry. Do y smiley face. I'm not going to use notation that's not widely accepted in the mathematical community for derivatives. That'd be fun. But I'm going to go, it'd be fun to make up my own symbols and operators, but I'm not sure the people grading the exam would be real happy with me. I'm not going to confuse it anyway, because I'm going to be very precise about my notation. Okay, I'm just going to go ahead and apply the derivative operator to everything. Derivative of xy is x dy dx plus 1y. Derivative of sine xy is cos xy times the derivative of xy. Good news for us, we already did that in this problem, right? So do it again. I'll pause in just a moment so we can catch up. X dy dx plus 1y. So chain rule equals 0. Okay. Then keeping in mind our goal is to get all the dy dx's by themselves, I'm going to group them. Here's one, and be careful with your distribution there. So this is going to be x dy dx plus cosine xy dy dx. I don't know if it helps you or not. I like putting parentheses around the dy dx's. Okay. Now, what I'm going to do in this next step is I'm going to jump everything that doesn't have a dy dx on it over to the other side with the opposite sign. So I'm going to go equals negative 1y, because that's this one moved over to the other side. I'm going to do the same thing with y cosine xy. Question? On the left, should it be cosine x squared y? Here? Oh, good point. Good point, good point, good point. This should be an x in front of that. The x doesn't go into the cosine, but it gets put on there, so it should be an x on the front. Yes. Thank you. You okay with me doing 2 steps in one now? We'll pause if it doesn't make sense. But dy dx is equal to fraction negative 1y minus y cos xy divided by x plus x cos xy. Okay. What I'd like you to make sure you try tonight or try over the weekend is the 3.8 day 1 homework. It's listed on your homework sheet as something like 5 to 41 odd. We'll talk more on Monday. Have a good weekend.